All right, you guys, I am very excited for this episode. We have for you guys Jamie Whitfield, and I know I'm going to learn a lot. So I'm going to be taking notes. Amanda's taking notes. We're going to have a lot of fun nuggets, I know, to learn from this episode. Jamie, thank you so much for joining us.
Thanks very much for having me.
So I prepped Jamie on our two truths and a lie. Our listeners have heard your intro. Before we reveal too much about your background, why don't we dive straight into your two truths and a lie, Jamie?
Okay, so my two truths and a lie. I played hockey growing up
Okay.
as a Canadian. I am related to a member of the Beatles,
Oh,
and I played in a punk band in high school.
okay.
Hmm.
These are all good ones. Where are you zooming in from today?
So I'm based in Australia. So I've lived in Melbourne, Australia for the last 6, 7 years.
Okay.
So despite being Canadian, hence the what I'm told is a relatively thick Canadian accent, at least by Australian standards. I call Australia home now.
Yeah. Oh, that's great. Um, okay. Well, you said Canada, and I feel like they definitely do hockey for sure up there. And I don't know, I could see the punk band thing being real. I'm gonna go with member of the Beatles, related to a member of the Beatles' life, but don't tell us the answer. Amanda, what are you thinking?
I'm gonna go out on a crazy limb and say it's the hockey thing because maybe that
Oh,
was like thrown in there to throw us off because we
maybe
would
he
think
was, yeah.
Canadians play hockey.
What's the other one? There's hockey and there's something just like hockey, but it's not on ice, right? Never
Lacrosse.
I
mind.
mean,
Maybe
there's field hockey and there's
field
also
hockey.
lacrosse,
That's what I'm thinking of, field hockey.
all of which are somewhat similar. Yeah.
Okay. Oh boy. Okay. Well, before we like I said, won't reveal the answer yet. Listeners are gonna have to wait till the end to find out if Jamie is related to a member of the Beatles or not, potentially. Did he play hockey or was he in a punk band? Why don't we take it back a little ways and we might reveal some of these truths or lies. What was your upbringing like? What got you excited about science and getting into specifically the science of working with endurance athletes and performance?
Yep. So I've always been sort of a competitive athlete myself. And so I think like a lot of athletes, there's a certain inherent what's going on with my body, et cetera. And especially with things like running as an example, and cycling, like why do we train the way we do? What are we doing? What systems are we hitting? And so those were all things that I think I was pretty interested in from a relatively early age, so sort of high school. But I originally thought I was going to go to physiotherapy school. That was sort of my plan and direction. I unfortunately had a knee injury when I was in high school, and so had to go to physio for that, obviously. And while I was sitting there, I was like, oh, this seems kind of interesting. This seems like something I could do. So I went to school for kinesiology, and the plan all the way through all of undergrad was physiotherapy, and it was fairly single track on that. And it wasn't till probably my last year where sort of I got the advice, well, you should probably have a backup option, cultivate different things. And at that time, I was taking an exercise biochemistry course, and I really, really enjoyed that. I liked how all the different energy systems sort of turned off or turned on at different times, and how that shifted with exercise and different intensities and all the different points of regulation. And I think that really appealed to sort of my analytical mindset. And I think it sort of connected to that earlier interest in sort of what's happening in my body. And so I did a honors research project with the professor, John Kowalchuk, who had taught that course. And I probably had only been in that for maybe a month when I was like, this is more what I want to do than physio. And so I ended up going to grad school. I did my PhD at a university called the University of Guelph. It's about an hour west of Toronto in Ontario in Canada. And I did that under the supervision of Professor Lawrence Spreet and Professor Graham Holloway. And yeah, the rest is sort of history, I guess.
Awesome. And post grad school, PhD, what kind of research did you get involved in? And are you still teaching now to this day?
So I don't do any teaching
Okay.
other than sort of guest lectures. I'm 100% research in my current role. So my sort of thesis and my grad work was all based on different nutritional interventions and supplements and models of changing energy availability and changing energy demand in the system. So that's sort of a fancy way of just saying how much energy are we using and how are we producing it, and how does that connect to sort of exercise and performance and overall health. And so we did that with a few different nutritional supplements. I also used a genetic rodent model for one of my projects to sort of expand upon some of those basic mechanisms. And then I knew that I wanted to continue on with that sort of avenue of research, but again, sort of connecting to that earlier sort of love of sport and connecting those two things. So taking that basic mechanisms of understanding what is happening in the body, but applying it directly to a sporting question. So I moved to Australia to join the lab that I'm currently in. So it's the Mary MacKillop Institute for Health Research, and that's at Australian Catholic University. And so I work with Professor John Hawley and Professor Louise Burke, and they're probably two of sort of the leading lights in this space in terms of connecting that exercise physiology understanding with that nutritional understanding and really working with sort of world-class athletes and applying some of these techniques and mechanisms and exploring it in an athletic population. So that's really what brought me here, and it's certainly what's kept me here as well.
Awesome. I just finished my IOC 2-year diploma with Louise Burke.
Great. So you already know she's fantastic.
She's the boss. She's got a lot of knowledge in her brain is what I will say. She's a smart lady.
She certainly is.
So with the kind of research too, and a big focus on that training adaptation piece, I have so many questions around this. I know you mentioned dietary manipulation, supplement for training adaptation. I mean, where do you want to start? I'm like curious about both of these avenues. So
I think to a certain extent, it's kind of hard to divorce the two. I think anybody that's ever done sport at any level knows that it's hard to separate nutrition from training, because you need one to support the other, whichever way you look at it. I think the benefit to the group that I'm in currently and the work that we do is that we take quite a holistic approach to things. So it's not necessarily separating the two. It's looking at how we can manipulate nutritional interventions, whether that be diet, supplements, or other things, to improve outcomes, specific. And I think for us currently, endurance sport is definitely where we're focused on. And I think that's probably just partially just, my background as well as others, that tends to be what attracts us. So we've done a lot of work looking at specifically low carbohydrate or ketogenic diets. That's something that we've been working on quite heavily for the last 5 or 6 years, and looking at how manipulating that can potentially impact exercise performance. So the basic idea there is that, in simple terms, you've got two major fuel sources to produce energy in your body. You've got carbohydrates and you've got fats. In different scenarios, you could potentially argue, protein, ketones, and other things. But for the general public, most of the time, those are your two major metabolic fuels. And so despite the fact that carbohydrate is something that everybody, they're told, make sure you're taking gels, make sure you're taking sports drinks, whatever the case may be, you don't actually have very much stored within your body. For context, circulating in your blood, you've got about 4 grams of glucose or sugar. So that's, a teaspoon, which is tiny when you consider you've got potentially 5 liters of blood. In terms of glycogen, the actual carbohydrates stored within muscle and liver, there's only about 400 to 600 grams of that stored in the body. So it's a relatively small amount. in contrast, on the fat side of things, even in, you know, a very skinny marathoner, you know, Eliud Kipchoge or someone of that ilk, there's basically limitless amounts of fat, even in that very lean individual. So potentially, if you could operate at a high intensity off of fat using that as your fuel, that in theory could be a limitless fuel supply. Whereas we know that with carbohydrate, because there's such a small amount, you're going to run out of carbohydrate if you don't take in extra fuel, you know, those gels, those drinks, in about, you know, 90 minutes to 2 hours, depending on the intensity. So that is quite finite. And so that sort of begged the question of, why aren't we better at using fat? And are there different strategies that we can use to sort of improve our capacity to utilize fat, but also hopefully keep our ability to use carbohydrate? And that sort of stems from a lot of work that was done by Louise, my former mentor, Lawrence Spreet as well, showing that if you consume a high-fat diet for, say, 3 to 7 days, you improve your ability to use fat, so you can produce more energy using fat as your fuel. So again, using sort of a car analogy, you're filling your car with fat here, and that's what's running the engine. But the flip side to that is you turn off your ability to use carbohydrate. So you're shutting that side down. And again, using a car analogy, carbohydrates your high octane fuel. If you were an F1 car, this is what you want to be putting in it. And that's because it's a more efficient fuel. So one of the things that gets talked about a lot in endurance training and athletic parlance is VO2 max. So the amount of oxygen you can consume per minute. When we look at it in terms of a rate, so how much oxygen you're consuming at a given period of time, when you're burning 100% carbohydrate, as an example, you're using less oxygen. Whereas with fat, you're using more. So it becomes a more efficient fuel. So again, the idea with training is that you want to become more efficient overall, and fat does the opposite effect. So it makes you less efficient to run the same speed. So if you were, you know, a 40-minute 10K runner, you could still be running those 4-minute Ks, but it's at a higher percentage of your maximum capacity and may potentially also feel harder. So that's sort of the very long-winded answer as to how we've sort of got into that space, is this sort of premise that there's an untapped potential with fat. And so we've sort of explored different durations of diets. We've started doing things like reintroducing carbohydrate for 24 or 48 hours prior to a race, with the idea that hopefully you get that sort of fat adaptation, but then restore the carbohydrate and hopefully turn that side of things back on. And so that's sort of the area we've been in for probably the last, I'd say, six or so years. And then the new sort of evolution out of that has been looking at sort of a low energy availability diet. So the flip side is, as opposed to just restricting carbohydrate, what if we restrict energy short term and, you know, potentially induce some body composition changes, but then restore energy availability prior to key races or a key test, and sort of see, can we improve the economy and performance that way.
Interesting. So jumping back to the 3 to 5 days of higher fat diet, not adding in the carbs before, you mentioned it being less efficient because of a higher oxygen demand. Are they taking in more respirations per minute?
So it's not so much the respiration rate per se, so the ventilation. It actually gets down to the basic biochemistry of it. So in order to completely break down or oxidize a fat to produce a given amount of ATP, you actually release more ATP from fat, but to burn it, it comes at a higher oxygen cost. So it's basically, again, getting down into those metabolic pathways, that sort of Krebs cycle and all that good stuff that everybody learns in high school and then hopes they never need to remember again. Those sorts of things, and then beyond in terms of the actual the mitochondria and how it's actually producing energy. So the sort of scientific name for it is the stoichiometric ratio. But so if you actually write that sort of balanced equation from first principles, you need more oxygen to burn fat or lipids to produce a given amount of energy. So it just comes down to the efficiency of the system. So it'd be no different, again, if you think about, if you go to the gas station, you've got different octane level of fuel. Same general principle. Some are going to burn more cleanly than others and release more energy as a result.
And so in the situations where you've added carbohydrates in kind of at the last day before the event, what were the results performance wise?
So we did I think from my opinion, heavily biased, a cool study looking at that exact question. And basically what we did, so this was a population of really well-trained race walkers. Australia has an outstanding tradition in race walking. And so there's a big culture for it here. And race walk is also quite unique in my experience on the global scene, that athletes from all countries tend to collaborate and work closely together and train amongst each other. Perhaps because it is sort of a niche sport, whereas you don't really get that to the same extent in other sort of athletic events, track and field. So we brought elite race walkers from around the world to Australia. They were based here, and it was a training camp environment. So we were able to control everything they ate. We provided them every single meal. Everything was individually weighed out per participant. So we had exact ideas of what they were consuming at all times. And we captured everything they were doing in terms of training, et cetera. And so for this specific test, this was sort of a 7 to 9 day intervention. And then they reintroduced carbohydrates for 24 hours prior to doing a 10,000 meter track race. And because we were based at the Australian Institute of Sport, they've got a really great setup there that the lab is maybe 400 meters away from a world-class track. So we were able to have these individuals come into the lab, do our sort of traditional battery of tests. So this involves, being on the treadmill with the mouthpiece on, so doing indirect telemetry, measuring oxygen consumption, calculating energy expenditure and fuel utilization. And then they were able to just jog over to the track and immediately go and race. Cool. And so what we saw was we had these athletes repeat it at the end of the sort of ketogenic diet, so that low carb diet. And we showed that, similar to what we've found previously, these athletes were able to increase their capacity to use fat as a fuel substantially. So some of these guys get up to, 1.5 to 2 grams per minute, which is, to our knowledge, some of the highest rates ever reported in the scientific literature. So really impressive ability to use fats. But again, they shut down that carbohydrate. And then after we've reintroduced it for 24 hours, they're sort of at a middle point. So they're not back to where they were prior to the diet in terms of being able to shift between those different fuel sources. So that's what we call sort of metabolic flexibility, being able to choose which pathway you activate based on the circumstance and need. But they still retained some of the fat adaptation, but some of the inhibition of that carbohydrate side. So they were sort of in the middle between the two. But what we saw was that performance was still negatively impacted. So we've done, I want to say, maybe 7 in a series of studies looking at different manipulations of carbohydrate availability here. So they're called the supernova studies. And so again, all in race walkers, some with males, some with females, some with males and females. And we've seen the same thing across basically every single study, that if you look at the difference between the improvement the individuals get on the high carb diet to the impairment the ketogenic athletes get, it's about a 7% swing.
Wow.
So typically we see our high carb guys improving by about 2 to 3%. And then we see the ketogenic people have a decrease in performance in anywhere between sort of 3 to 5%.
Wow.
And so that's massive. In the context of whether you're looking at the 100 meters or the marathon, at the Olympics, typically first and third is separated by less than 1%, regardless of race distance. So something that you can do as simple as changing your diet for 7 days that is going to decrease your performance by, 3 to 5%. that's pretty substantial,
Yeah.
because within that time frame, we're not expecting huge changes in training status for these individuals because they're already so elite.
That's so interesting. And if someone were to follow, if you may or may not have studied this, so let me know, but if someone's following that high fat diet for the 3 to 5 days before, and then they have a long event and start trying to utilize carbs during, have you guys looked at that?
So we haven't looked at that question specifically, but there are other researchers that have. So again, one of the key caveats I need to mention here is that it depends on the intensity of exercise that you're doing. So if you were doing sort of ultra marathons, for example, where it's a lower relative intensity, something like a ketogenic diet or a low carb, high fat diet might be completely fine. From sort of a first principles approach, again, we sort of see that fuel switch in most people between sort of 60 to 65% of their VO2 max. That's where you shift from using predominantly fats to predominantly or exclusively carbohydrates. And again, that's because it becomes a more efficient fuel. We can push that upwards with that adaptation, so you can go higher, but it's still, in at least in our hands and in the hands of a few other research groups around the world, we've never been able to show high intensity performance is maintained on a ketogenic diet. If you adhere to it for a very long time, there's some evidence to suggest that your muscle actually remodels further on the carbohydrate side. So it actually decreases the expression of some of the proteins and enzymes that are involved in carbohydrate metabolism. And I think that's similar to most things, that your body's pretty good at sort of regulating and changing to say, I'm not seeing this in the system, therefore I don't need to maintain this.
Right.
And we see the same thing on the fat side of things, that after, as little as 1 to 3 days on the diet, the proteins and the enzymes that are involved in the breakdown of fats at the level of the muscle, those start upregulating and increasing. So your body's very, very good at adapting and fine-tuning that system. So in terms of maintaining the ability to use carbs throughout, I think that would probably be limited, but we haven't tested that directly.
That's so fascinating. And when you say kind of move that maybe fat burning ability higher, is that in reference to like the respiratory exchange ratio?
So respiratory exchange ratio is sort of a proxy that you can use to determine what sort of fuels you're using. So again, as with anything, there's sort of caveats and limitations to it. But if we look at it from strictly a carbohydrate and a fat scenario, a 0.7 we assume to be 100% fats. A 1.0 we assume to be 100% carbohydrates. So what I mean when I say you can push that needle is, instead of sort of hitting your fat max, so the maximal rate of fat oxidation and what intensity that corresponds to. So instead of saying that occurred at 64% of VO2 max, we might be able to move that up to say 70 to 75 potentially. Again, there are limitations to that as well, because you're consuming more oxygen to burn the fat, so that it's to a certain extent artificially moving things. But the idea is that we can become better at using fats. There's no question to that. And in some scenarios, again, that may be completely fine for the intensity that individuals are competing at. But for Olympic sport, it doesn't appear to be beneficial. And so again, connecting it back to race walk, one of the unique things about race walk was previously it was the longest event on the athletics calendar. So they typically used to compete over 20K and 50K. The 50K isn't competed at the Olympics anymore, but they also compete at 20 and 35. So regardless, you've got sort of events that are straddling that intensity limit around the marathon, both in terms of duration and distance. But the other unique thing with race walk is it's held on a closed course. So there's more opportunities to provide fueling for race walk athletes compared to a marathoner, where a fuel station might be every 5 kilometers. Here it's every 1 to 2.
Okay. Interesting. This is also so neat. So with that increasing the fat adaptation potential, thinking about an athlete's training season, year, structure. I know maybe this has changed a bit. It's like kind of what I had learned at school is like that post-season kind of preparatory phase, working towards increasing that fat burning potential, maybe doing some of that, what is it? Train low, like or sleep low, train low, those kind of protocols. What are your thoughts on those training? Well, one, training time a year potentially. Does it just completely revert once we get into race season? And two, is it going to benefit us in any way, or does it seem to do that? And applicable to men and women? Question mark.
Yep. So that's definitely a major caveat, is a lot of these studies, not so much the race walk stuff, because we have done a lot of work with female athletes in those studies, and we've shown the same thing.
Okay.
So the first two studies that were published by Luis on this question, the first one was entirely males, and that was a 3-week dietary intervention. And the second study was a mixed cohort of males and females, and the results were exactly the same.
Okay.
So at least in terms of that dietary adaptation piece, we're fairly confident that applies equally to males and females. But yes, 100%. There are limitations in sort of extrapolating, because a lot of it is done in sort of a convenient sample. So if you read most papers, it tends to be, recreationally active males between 18 and 21. And that's primarily because it's work that's done at a university where there's a lot of recreationally active males between the ages of 18 and 21.
Right.
So it becomes a bit convenient there. But so there definitely does need to be some work done in females. In terms of the train low and sleep low work, the idea here is that by manipulating the carbohydrate that's stored in your muscle, so your muscle glycogen, if you commence exercise with a low glycogen store, your system perceives that as more stressful in simplistic terms. So there's a protein called AMPK, and basically that is, you can think of it as sort of a metabolic fuel gauge. And so it's a kinase that senses energy levels within a cell. And when energy levels are low, it activates pathways that are going to produce energy. So your carbohydrate oxidation pathways, et cetera. And when energy levels are high, it's going to turn those off and turn on other pathways. So it sort of regulates how things are turned on and off. So you can think of it as sort of a series of switches throughout the muscle. And so the idea here is that we've done some work led by Nolan Hoffman, one of the research fellows in our group, that looks at how that protein, AMPK, can actually bind and interact with carbohydrates, so with glycogen. And the idea here is that potentially when you don't have glycogen, that AMPK is no longer attached. And so that's going to activate different cell signaling pathways. So that's going to turn on a different series of switches and pathways. And AMPK is really important when we think about training adaptation. So it's one of sort of the classical pathways that when we look at energy stress and how that activates things in the muscle, that's one of the proteins that researchers typically target. And that's because it's linked to the creation of new mitochondria, so the process known as mitochondrial biogenesis. So when we think about train low, one of the ideas here is that potentially for the same given bout of exercise, if you commence it with lower stored energy, lower stored carbohydrate in the muscle, you may turn up those signals. So amplify the response that your muscle is getting to that bout of exercise. So you don't necessarily have to work harder in terms of, watts if you're a cyclist, or run at a faster pace, etc. But your system perceives that as more stressful because there's more sort of disruption to cellular homeostasis. So how everything is being balanced and regulated. In terms of how that works in a scientific setting versus how that works in an applied setting, that's where things get a little bit murkier. So we can take, we're somewhat limited with a scientific study that in order to measure these things, you need to take muscle biopsies. And that's obviously an invasive procedure. Not everybody's willing to do that, but you're also limited in terms of the time points you can capture. You can't do one every 20 minutes or something like that. You've got very finite time points that you can take. So typically, people will take immediately before exercise, immediately after exercise, and then say 1 hour, 3 hour, 5 hours to sort of get a bit of a time course. And we can show with these studies that you get a really nice pathway activation that things turn on and then they turn off. And from a train low perspective, there's some really nice data out there from John Hawley, who I work with, showing that you do get an augmentation or an amplification of these signals. So the signal is turned up when you say start with low glycogen, and there's different ways that you can do it. One of the ways that you mentioned is sleep low. So you do a bout of training in the evening and then don't consume much carbohydrate, go to sleep, and then do your next bout in the morning. So you've slept overnight with a low glycogen store and then commence your next exercise. But a lot of elite athletes are doing this inherently without even really thinking about it. If you're training twice a day, or if you're a triathlete, potentially 3 times a day, or however much, chances are some of those bouts you're going to have low glycogen stores just because you can't replenish that glycogen that quickly. So if you train in the morning and then had another session at lunch and then another session in the afternoon, those last 2 sessions are technically going to be train low even without you thinking about it. So in terms of how that connects to practice, I don't think there's strong evidence to suggest that that is going to overall enhance performance. I think as it stands right now, it's sort of equivocal that the performance is about the same.
Yeah.
There's some studies that show there is an improvement in performance, some that show there isn't. So I think one of the things is, when you think about it from an athlete practitioner standpoint, is what you said is completely correct, is what phase of the season are you in? So, if you're in that base phase, that's definitely something that you can consider incorporating, that it's a different way to stress the system, if you will, and potentially get an adaptation, with the caveat that it is a bit harder on the body. At least I've found when I've done it previously, is that those sessions do feel harder. And so, you don't want to be doing that every single day. Some people inherently like fasted training, and if they do, great. But I've always found it to be harder than doing a workout properly fed and fueled. So you would want to do that sort of in that sort of preparatory phase, not as you're moving into sort of a competition phase, where you want to probably be shifting things to making sure everything is well fueled and you're recovering to the maximum extent and sort of getting sharp, if you will.
Yeah. Do you think in doing it in that base phase, is that going to move the needle enough to help with the performance piece?
Again, it's hard to say. Right now, the literature would probably suggest equal effect to standard training. But again, this is looking at it from, studies that may potentially have a group of 8 athletes. Again, as we mentioned earlier, probably predominantly males. And so then we're looking at averages across a group. And so I think the biggest thing is, when looking at working with athletes, is figuring out what works for the individual. So again, for some individuals like myself, it could be the worst thing ever. I was miserable when I tried to do these in my own training. For other people, as I said, who enjoy fasted training, it might be great. And so they may get a better response from it as well. And so when we look at it just from a group level in a scientific paper, you potentially miss some of those nuances where, as a great example, some of those studies we were talking about earlier with the ketogenic diets, there are, the odd individual that goes the other way, that has an improvement in performance. Are they different? Maybe. We don't really know why that variability exists. It's just all people are different in terms of how they respond to different things. So it's sort of teasing that apart. And I think that's where things are a lot harder for coaches than they are perhaps for the research scientists.
Yeah, very interesting. I want to make sure we touch on supplements too. We've talked a bit about the dietary adjustments. Tell us about the supplement arena with regards to training adaptation impact.
Yep. So this is sort of the area I've think probably spent the most time in. So through my PhD, I did a lot of work looking at dietary nitrates, so beetroot juice. And that's because when I was doing my PhD, that was sort of the in vogue supplement. That was the one that everybody was talking about, sort of surrounding the 2012, 2016 Olympics. That was the big one that everybody was kind of talking about. And so we did a lot of work looking at beetroot juice. And so again, thinking about it in context to what we've already discussed, the major premise with beetroot juice was that it was going to decrease the oxygen cost of exercise. That's sort of the fairly well accepted mechanism at this point. A bunch of different research groups have shown this. This was primarily pioneered by Andy Jones at the University of Exeter in the UK, who led a lot of this early work, but it's been replicated now by numerous groups throughout the world. So it's a fairly robust finding. And so that's really unique. Again, from a classical perspective, we assume that the oxygen cost of exercise is fixed. So for something like cycling, as an example, it's usually in the realm of 10 to 11 milliliters of oxygen per watt cycling. So if you do, 300 watts, you can do the calculation of what that should cost from an oxygen perspective. So something that you could take acutely, 90 minutes to 2 hours before exercise, that is going to decrease the oxygen cost. That was sort of very exciting and very new. And so there was sort of a host of different possible mechanisms. And so one of the mechanisms that really caught the interest of myself and also one of my supervisors at the time, Graham Holloway, was the idea that it could impact mitochondria. So again, thinking back to everybody's sort of grade 12 biology, it's the sort of unquote powerhouse of the cell. It's this little kidney bean shaped structure that everybody sees in those diagrams in their textbooks. We now know that mitochondria do a lot more than that. But from a basic premise, the idea that you could take something acutely and that may impact the mitochondria and how it's actually producing energy was really interesting. And so there was some work led by Philip Larsen, who is, I want to say, in Sweden. I've forgotten what university he's at currently, but suggesting that was how beetroot juice was acting. It was impacting the mitochondria. And so again, the flip side to that, what we had been discussing with ketogenic diets, was that this was potentially allowing you to produce more energy. So ATP, that's the currency of the cell, if you will, for a given oxygen cost. And so that's directly tied to what's called mitochondrial efficiency or PO ratios. And so that was a really interesting sort of idea and something that we were really scratching our heads about. We could see it, with a long-term supplementation, okay, potentially, your body's reacting to this. It's changing the expression of different proteins or enzymes or something like that. But to have something that acutely impact the mitochondria was really interesting. So that was what we tested. And we were unable to show an improvement in mitochondrial efficiency. And that finding has now been replicated by a few other groups as well. So it doesn't look like it's working at the level of the mitochondria.
Okay.
But that was sort of my first foray into that. And so we've done a few different things now. We've actually combined beetroot juice with the ketogenic diet to see if those two things could sort of counteract themselves.
Yeah, interesting.
Spoiler, they didn't. But more recently, we've looked at ketones. So again, that's something that's become really popular and really big. And we've also looked at more recently a novel supplement. So it's a supplement called Urolithin A. And so Urolithin A is a polyphenol. So when people think about things like pomegranates, red berries and cherries, et cetera, green tea, those are all rich in polyphenols. And so ideally what happens is you consume these food items, these foodstuffs, and then they're broken down into the constituent parts. And hopefully the sort of bioactive ingredients increase and those, exert whatever influence they're having on the system. One of the problems, however, is that not everybody has the right gut microbiome makeup in order to fully digest and break down these products to sort of the key active ingredients. And so in the context of this specific compound, urolithin A, it's only about 40% of people that have the correct gut makeup in order to produce this this active biocompound. And so there's a company that has been able to isolate and synthesize the compound. And so by providing it in capsule form, you sort of circumvent that limitation. And so they were able to show that by consuming these capsules, you were able to increase the concentration of urolithin A in circulation. It also gets into muscle, which is a critical step because it doesn't always work that way. And they found in elderly individuals that this improved sort of proxies for performance. So grip strength, the ability to get out of a chair and walk. So things that are important for daily living for elderly individuals. And so that led us to sort of ask the question, well, how's this working? And there was some data produced showing that it might be acting through the mitochondria. So again, that energy production pathway. And beyond sort of just energy production, what it was showing to do was induce a process known as mitophagy. And so basically this is the recycling of mitochondria. So again, as I alluded to earlier, mitochondria aren't just these static little kidney bean shaped organelles in a cell that are just sitting in place, producing energy, doing their thing. They're constantly moving, they're constantly merging and separating, and they exist as a cellular network or reticulum. And so they're constantly undergoing these processes called fusion and fission. And over time, you get, same as anything, defective proteins or damaged proteins. And what's happening is there's a continual turnover of those. And so that's what this process known as mitophagy is. So it's the disposal of damaged components of mitochondria. And this compound was shown to increase that process. So it was being able to recycle those damaged mitochondria, and hopefully the end result of that is a healthier overall network that is able to produce energy more efficiently across the network and support the demands of exercise and daily life. So for us, we were really interested in this as, could we take that and apply it to an athlete population? So we know that energy production, mitochondria, et cetera, that's going to be very important for endurance-based athletes. We know that being able to produce new mitochondria, so that mitochondrial biogenesis pathway, that's a critical part of training adaptation. But could we potentially connect these two pieces and look at how this supplement could support training in elite endurance athletes? And so we've just completed a study affectionately known as Enduro, so endurance and urolithin A. And what we did was we recruited 42 highly trained male athletes. So again, a caveat here being that it is a study performed in males. And that was because we had them for a month in a training camp. So we couldn't time testing to different menstrual cycles and menstrual phase. And so unfortunately, we couldn't account for females in this specific study. But we had athletes, again, with dietary control, something that our group is very, very good at. So controlling, similar to what I described before, everything they eat, knowing exactly what they're consuming at a given time. And we had these individuals separated into two groups. So we had one group that performed 3,000 meter time trials. So they were predominantly middle distance and long distance athletes. And then the second group who had muscle biopsies taken before and after the study. And so what we did with these athletes was we took them to altitude in Australia. So unfortunately, we don't have gigantic mountain ranges here. So we are somewhat limited there. So we took them to about sort of 2,000 meters, which is, a bit higher than Denver for people who are in the US. And we had them train there for 3 weeks while consuming either the urolithin A or a placebo. And one of the other things we did was each week we would have them do a hard downhill run. So if anybody's ever done Boston and then tried to get down to the subway or anything like that afterwards, you see all those great photos of people, crawling down the stairs. running downhill induces a lot of damage to the legs. It's that eccentric loading that just absolutely beats up your legs until they're like mincemeat. So we had these athletes do that every Monday for that 3-week period. And it was around between 4 and 5K, started off quite steep, between 7 and 11% for the hill. And it averaged around 4 to 5% for the full 4 to 5K. So we had them run down, we drove down, picked them up, drove them back up, took blood markers for the next 36 hours, and then had them continue with their training. And so the idea here was that we wanted to test whether this supplement could potentially help recover some of those damage markers, so limit the damage, or potentially help with the recovery aspect. So when we are inducing damage as part of training, can these athletes bounce back better in order to be able to show up the next day and do whatever is required of them for training, and the next day, and so on and so forth? Because I think that's the key thing, again, from a practitioner standpoint, is that consistency, being able, it's great if you can do one heroic world-class workout, but if you can't do that day on day on day, that's the differential. And so after we did all that, we returned back down to the Australian Institute of Sport, and we repeated all those tests. So similar to what we've done in our previous studies, we've done aerobic capacity, so VO2 max, running economy, but we also had in this study muscle biopsies, blood samples, etc. And so what we were able to show was that while performance wasn't different between the Urolithin A group and the group consuming the placebo, the blood markers for damage after that race were decreased in the Urolithin A group. And what was really interesting was their rate of perceived exertion was also decreased.
Oh, nice.
So even though they're running the time trial together, all the athletes, on a group average level, the athletes that were consuming the Urolithin A felt like they were working less hard, and there was less damage markers increased in their blood. And we're still sort of analyzing the muscle data, but what we've seen so far is there doesn't appear to be a difference in mitochondrial function. So again, there's sort of two parameters that we look at when we consider mitochondria in the context of exercise. One is sort of the number, so mitochondrial content, again, and that's linked to that mitochondrial biogenesis. So turning on those different pathways, producing more mitochondria. So ideally, you can produce more energy or share the production of energy across that network. And the other is mitochondrial function. So this is how those individual mitochondria are actually producing energy. And so what we can do is we can use a technique called permeabilized fibers, where we take little pieces of the muscle and we provide them with substrates, so in this case carbohydrates or fats, and we can actually see how the muscle respires, so how it consumes oxygen to produce energy. And from there we can get an idea of how those mitochondria are functioning and how they're performing after that supplement or a given intervention. So in this case we didn't see a difference with Urolithin A. But we've done a technique called proteomics, which looks at the global changes in protein expression across the different cohorts. So again, Urolithin A or placebo, and it does appear like the mitochondrial associated pathways are upregulated. So targets and proteins that are associated with the mitochondria, the expression is increased. And so that's something that we're still in the process of delving through that data and exploring a little bit further.
Cool. And so with the Urolithin A, is that something you mentioned in polyphenols? Does that mean that there's Urolithin A in all dark, like fruits and veg, or?
Yep. So maybe not so much the fruits and veg, but certainly anything that is rich in polyphenols should be a precursor for polyphenols and specifically Urolithin A. But again, the key piece is whether or not you can actually get to that step. So being able to break it down completely to that point, that's the key limitation, and not everybody has that gut bacteria.
Right.
So that's where something like a capsule may be beneficial, and it's the same as any other mineral. If you're deficient for whatever reason, there are ways to circumvent that.
And with your study group, were they doing the capsule variation or were they diet focused?
So it was a capsule.
Okay.
So yeah, so they consumed 1,000 milligrams per day.
Okay. Wow. Nice. And makes me think, like, definitely have heard talks around tart cherry juice
Yep.
concentrates, that kind of, I would imagine that maybe has some urolithin, but again, like you're saying, can they produce it at the level of the gut?
Exactly. And so that's where we're sort of coming from, is that we think is probably a potentially similar mechanism of action. So a lot of that sort of early dark cherry work was looking at recovery. And that seems to be where we're seeing the most effect in the cohort that we studied. So we're not seeing huge shifts in performance, but we do seem to be pulling out pieces that are indicating a better recovery in those athletes. And so right now what we're looking at is looking at inflammation in these athletes. And that's something that we're diving into currently.
Cool. Very interesting. We have covered so much and I want to be mindful of your time. This has been amazing information. We'll jump to the two truths and a lie, reveal those, and then we'll do kind of a tie up with you, find out where people can find you, follow you. But our two truths and a lie, we had played hockey growing up. You're related to a member of the Beatles, and that you played in a punk band. I was going with the Beatles one. Amanda said hockey. What was your lie?
So Amanda was correct. The hockey was the throwaway. So yeah, so I've actually never played ice hockey in my life, despite growing up in Canada.
So what sports were you involved in?
So as perhaps kind of came out, I'm heavily endurance focused, but growing up, I played basketball and played soccer until I was about 18. And then the shift was fully into track and field and cross country. And I ran varsity through university, and then continue to dabble a bit in that, as well as doing some cycling.
Awesome. And what was your punk band name?
So the punk band was called Last Man Standing. So I was in that until I think I was like 16. Yeah.
Nice. What instrument did you play, or did you sing, or?
So I played bass guitar, and anyone who's heard me sing can attest that I was definitely not a vocalist. So
awesome. And which Beatles member are you related to?
So on my father's side, so my family is originally from the UK. We are a presumably distant relation of George Harrison.
Cool. Did you get like a 23andMe done and they sent you a little email reminder?
No. Again, perhaps because of me getting really into music when I was in high school. I can't remember how it came up, but my dad was very heavily into sort of classic rock music. Cool. And specifically the Rolling Stones, whereas my mom was big into the Beatles. And so I forget how it came up, but it's, a second or third or something cousin of my grandfather.
Wow. That's awesome. Very neat. This has been such an informative episode. All kinds of fun stuff in here. Where can people find you, follow your work, attend any upcoming seminars, any of that stuff?
Yep. So not exactly sure when this will come out, but I am speaking at the Australian Physiological Society meeting in a couple of weeks' time. That's being held in person in Melbourne.
Okay.
So that's the last week in November, awesome. And it's being hosted by Australian Catholic University, which is great. Great. And then I'm also on Twitter, so J Whitfie, JWHITFIE, and so I'm relatively active on there. And then most of my publications and things can be found through Google Scholar. So just my name, Jamie Whitfield. And that should lead you to any of the publications that we've talked about today.
Perfect. Awesome. Well, thank you again so much for your time, Jamie. This has been a fascinating learning episode for myself, I'm sure, as well as our listeners. So thank you.
No, thanks very much for having me.